Thank you very much. I'm going to tell you about some new connection between things which we know from theoretical physics and from mathematics. Namely, I will introduce in particular way covariant phase spaces, which are quantum deformed, and I will show that you can relate with this notion a notion of Hopf algebroids, which is a kind of generalization of Hopf algebra, and you will see in which sense. In some sense, the unit element of Hopf algebra is becoming just some non-commutative algebra, subalgebra. So I wrote this paper with my student, PhD student, former PhD student, Mariusz Woronowicz. There is in Poland so-called Big Woronowicz, and it's not that one. And with Croatian physicist Zoran Škoda. So we know people who are interested in quantum symmetries, they know that there are just two notions: Hopf algebras as the algebraic generalization of the notion of a symmetry for deformed theory, and quantum spaces. But the point is how to which notion should be attached Heisenberg algebra. Of course, Heisenberg algebra is an algebra, so it is a quantum space, but it has some additional structure. So this additional structure can be related with this notion of Hopf algebroid. Now, not every quantum phase space I will be considering here. I will be considering such quantum phase spaces which are obtained from the notions of quantum symmetry. So maybe if some of you did hear about the Suryo approach to the description of elementary systems, so this is a kind of quantum deformation of this approach. What is the advantage of such approach? That you get covariance built in such a structure. So it's because, for example, if you say what is Minkowski space, you can say it's just four numbers, but you have to say they transform as a Lorentz vector. Yeah. So also here, the quantum phase space should have a correct transformation properties. After, because I said I can apply it to the deformed phase spaces, I will show how you can obtain in such framework the kappa-deformed quantum phase spaces in 4 dimensions, because this is the usual dimension you consider. And I will consider just 2 kinds of this kappa-deformed quantum phase spaces. Generalized phase space describes you the system which has a translational degrees of freedom and spin degrees of freedom. So this translational spin degrees of freedom will give you 10-dimensional coordinate manifold. So this is this space H 10, 10, where you have 10 for coordinates and 10 for momenta. And the standard kappa-deformed quantum phase space is just the deformation of the usual Heisenberg phase space with the coordinates x mu, p mu. These notions below, target maps, antipodes, and coproduct gauges, are just things which are related with the formalism of Hopf algebroids. So I will just give it for this case of standard kappa-deformed quantum phase. I will provide these notions and show discussion after. So now let me say, as a kind of introduction, how looks the situation with symmetries if you consider just 3 basic physical theories in classical mechanics and in quantum mechanics, and quantum field theory, but without quantum gravity effects. Then you just use classical Lie groups and classical Lie algebras. in classical case, usually use matrix realizations. In quantum field theory and in field theory, use usually differential realizations. Now, when you pass to the system with quantum gravity effect, so besides h different from 0, you have to assume that the Planck constant is different from infinity. So this quantum gravity effect, there is a kind of general conviction that this will imply some non-commutative structure, what leads to the symmetries which are quantum symmetries. So you have to discuss quantum Lie groups in place of classical quantum Lie algebras. Here, these two objects are dual in the sense of Hopf algebras, and the realizations of these objects are also on non-commutative spaces on so-called Hopf algebra modules. These Hopf algebras just denote the algebraic generalization of standard notion of groups and Lie algebras. And they are described by the following elements. This is the algebra A, multiplication rule, coproduct, antipode, and counit. So B algebra is obtained from Hopf algebra if you don't consider antipode, or co-inverse, some people say. And of course, in the B algebra is embedded the algebra. This is the algebraic sector, this algebraic sector. So now what is important that this algebraic sector, the coproducts, are describing algebra A homomorphically. It means they satisfy the same algebraic relations. For classical Lie algebras, then the coproduct is primitive, which looks like this. And from quantum Lie algebras is non-commutative, but in classical quantum groups is used the same. Here it's written in the following way. So you just multiply matrices in order to obtain the coproduct. So now the quantum space quantum space algebra is just some non-commutative vector space which has as generator some algebra V. In standard physics, then you have a commutative representation spaces. In quantum-deformed physics, non-commutative Hopf algebra modules. Now, these modules, they have to satisfy some algebraic consistency property. Namely, the Hopf algebraic action should involve the coproduct, and this is the formula how you act on the product of two elements of the module X and Y. Now, what is interesting that this Hopf algebra modules are just important class of general quantum spaces. In physics, which, as I mentioned before, due to quantum gravity effects, if we look for the physical origin, then you obtain the deformations of algebras, and for d equal 4, I mentioned just the Poincaré Hopf algebras and Poincaré Hopf Lie algebras. So here are Lie algebras. Here are quantum groups, and they are dual to each other. This is the enveloping algebra, and then the index Q denotes the deformation parameter, which usually among people doing some deformation theory, Q is related with Drinfeld-Jimbo deformation, but here I'm just denoting by Q an arbitrary deformation parameter. I'm giving here popular examples in the case of Poincaré algebra. So there is the so-called canonical theta mu nu deformation, where theta mu nu is just a constant tensor describing the commutators of non-commutative space-time coordinates, and kappa deformation, which is an example of so-called Lie algebraic deformation. Now, if we have such a framework, now appears the following question: how to describe in such a framework the quantum mechanical phase space before deformation or after deformation. So Heisenberg algebra. Here I have written the relativistic Heisenberg algebra with generators x mu and p nu. They satisfy the following algebra. You assume in quantum mechanics that h is a C number. It is a universal constant, and what is important that it is the same if you consider all quantum mechanical states. So here should be a genuine number. Now, if you look at the coalgebraic sector, then in canonical phase space you can introduce just separately the coproduct for the coordinates and coproducts for the momenta. But if you want to check whether the Heisenberg commutators is satisfied by these coproducts, you will find a factor 2 here because this first thing will produce 1 times 1, and this with this, and this with this will produce also 1 plus 1. So there is a lack of homomorphism. So of course Heisenberg algebra is not a Hopf algebra. And there are 2 ways of going out from this situation. One is a little bit brute force treatment, that you introduce instead of Planck constant, Planck constant as a C number, multiplied by an operator with the primitive coproduct. But unfortunately, this leads to different values of Planck constants for different quantum states. For example, if you want to describe the action of this coproduct on the tensor product of 2 states, then you get factor 2. Another way is just to look for some freedom in choosing the coalgebra. And it could be cured the problem when you can introduce such a kind of coproduct, because this with this gives you again the Heisenberg algebra relation. So now, if you introduce the notion of B-algebroids, such coproducts are allowed. So I'm going to discuss you the framework of B-algebroids now. So now, if you have a Hopf algebroid, the structure of an algebra is more complicated. You have a total algebra A and base subalgebra, which is a subalgebra of this base of this total algebra. And there are 2 characteristic maps for algebroid structure. One is the source map, and second is the target map. One is homomorphic map, second is anti-homomorphic. And so every element of B acting on element arbitrary of A gives you multiplicatively some source operator or target operator here. So the main point is just this more general structure of the algebra. Now there is a coproduct. On next transparency I'll tell you that it is not completely the same coproduct. You have also antipode and you have a counit. Now, if we want to go back to physical examples, what would be assignment in relativistic physics? For example, if you have a Heisenberg algebra, then this B here will correspond to the coordinates, and the whole phase space is just algebra A. If you have extended coordinates by some Lorentz parameters and Lorentz rotation generators, then your algebra B will consist of x mu and these Lorentz parameters, which, depending on the deformation, have not necessarily abelian properties. And this is the whole algebra. So these are the coordinates, these are the momenta. Now, what is the property of the source and target map? They are commuting for arbitrary choices of these elements B belonging to this base algebra. And you can say that this notion of these two operators S and T, they introduce the algebra as so-called BB module. So it means that if you have such an action of elements on the left side and the right-hand side of acting on the element of A, then you have such a property. And in order to define the coproduct, one can use the notion of tensor product over non-commutative ring, which in this case non-commutative ring will be B. This coproduct has been introduced by Takeuchi. This tensor product over non-commutative ring can be, however, obtained from standard tensor products, provided we factorize, we introduce we divide by ideal the standard tensor product. The ideal is written here. It is here a lefty ideal. By the way, you can have two notions of by algebroids using or left or right ideals. I'm using here left ideals. And now you can say that in the language of the standard tensor products, the element belonging to this Takeuchi tensor product is obtained by the following elements H prime with the standard tensor product, which satisfy the following relation, where this S and T are these two operators characterizing the algebroid. So in this way, you get a non-uniqueness of the homomorphism map, and you can say that this freedom related with different choices of this H prime in this algebra looks like a choice what in this paper we called coproduct gauges. Antipode, this is an anti-algebra map which acts in inverse order on the product, and this is the property of this antipode if it acts just on the source map and the target map. The action of the antipode on the source map gives you target map. There is a possibility of choosing choosing the following map S, that SB is just natural inclusion B, and in such case you get the relation, the action of the T is defined just an antipode. So now one of the differences with Hopf algebra is that the co-unit is equal 0 only on those elements of A which do not belong to B. On all elements belonging to B, you have a co-unit 1. These relations are just some consistency relation between coproduct and antipode. There is some subtle thing that this left relation can be valid only on some projections of these coproducts within this family described by IDL. Here I have remarks that you can introduce two different algebroids, left and right B algebroids, depending on the way you introduce or right ideal or left ideal. So we choose right ideal because of some we use some formal calculations which were, so to say, without still realizing it, used for the right B algebroid. So now I'm going to the description of covariant quantum phase spaces. This this way of constructing covariant quantum phase spaces is known as the construction of Heisenberg double. So standard Heisenberg algebra can be obtained as a semi-direct product of two dual Hopf algebras. And by the way, this Heisenberg double is a kind of sophisticated name for a semi-direct product of quantum Lie algebra acting on the, the action of one Hopf algebra acting on the dual Hopf algebra. So now you have these two Hopf algebras, and if you want to generalize this construction to any dual pair of Hopf algebras, then you can use general structure. Duality requires existence of a bilinear map between the one Hopf algebra, one algebra, and algebra belonging to one Hopf algebra, as algebra belonging to the dual Hopf algebra. And this duality provides known from Hopf algebraic framework relation that multiplication in H determines the commultiplication in dual H, and commultiplication in H dual determines the multiplication. No, I should write here tilde on this side. So communication in H, multiplication in H dual. So you see that if you have one Hopf algebra, for example, if you have a quantum Lie algebra, you can determine quantum group from this duality. So this is just a convenience. Now, what is interesting that in this semi-direct product of these two Hopf algebras, the algebra which belongs to this, I denoted by H tilde, I think, quantum group, is a H module with the action of H, the following action of H, and this is the formula for the action which is consistent with Hopf algebraic action in Hopf algebra H tilde. So if we introduce the Heisenberg double algebra A, which is just a sum of algebra A and tensorial sum of A and A tilde, then I mean the basis of this algebra. So you can derive the cross multiplication rule using the formula, which uses coproduct in one algebra in one algebra in second algebra. So in this way, because inside of Hopf algebra H and H prime, the multiplication is determined, so the cross multiplication is determined by this formula. Now, I think main reason for, I would say, mathematical reason for validity of this construction is a general theorem that, which is shown by Lu. This is Shi Lu, not He Lu, that the Heisenberg double algebra is having a Hopf algebraic structure. So now I'm going to discuss such phase spaces which are obtained in such a way. So if they are obtained, the Heisenberg doubles of quantum Poincaré Hopf algebra and quantum Poincaré group. Of course, if I would introduce another coordinate manifold, I could introduce other Hopf algebras. Then in this way, I'm obtaining as Heisenberg double this quantum phase space. Now, what is nice that in such a case, the covariance is built into the construction. Now, if we pass to the case of kappa-deformed covariant quantum phase spaces, then first let us consider the general case of kappa-deformed quantum phase space with 10 plus 10 dimensions. Then you consider just kappa-Poincaré algebra, and I think the convenient basis, so-called bicross product basis by Majid-Rouek, where the bicross product consists in cross product structure of the algebra and coalgebra. So you have a right action of the algebra on the momenta, and the left coaction of momenta on the rotation generators. So now this is the notation for for this B cross product. And by duality, you get a structure of the group, which here the deformation sits only in this, so to say, commutation relations between these two elements. Here, this kappa also enters into the commutators, because here you get, here are coordinates, where you get a kappa-Minkowski space coordinates. Here you have Lorentz parameters. So now you get here L6. L6 is the algebra of functions of Lorentz parameters. So by duality, the T4 is dual, the momenta are dual to this momentum space coordinates. And non-deformed Lorentz algebra, because this is the case in Megit-Rueck basis, you obtain the abelian Lorentz group parameters. These parameters are commuting, are abelian, but they do not commute with x mu. So this is their feature. Now this duality relation, this scalar, this binary product, which you need for dualities, looks like this: the standard correlation of the bases in one Hopf algebra and the second Hopf algebra. So in such a way, you obtain just the generalized phase space containing translational and spin degrees of freedom. Now I'm here, in order to be concrete, I'm writing this Hopf algebra H, which is the kappa-deformed Poincaré algebra. So you see the only deformation, as I mentioned, is in the coproduct, in the commutator, in the algebra. It's only in the commutator of the translational sector and the rotational sector. The Lorentz sector is classical, and this is the Lorentz sector, and also the three-dimensional momenta are also classical. Now here you get the coalgebra sector, which is written here. There are some deformations. Here are just co-units and antipodes. Now, by this Hopf algebraic duality, you get the kappa-Poincaré quantum group, which already was formulated in 90s. Then this is the algebra sector. These are the kappa-Minkowski coordinates here. These are the Lorentz parameters, so to say, Lorentz rotation parameters. Here is the non-vanishing commutator of lambda and x. Here, this is the typical, this construction, which is this basis, which has been introduced in such a way, leads to the same coalgebra sector as in undeformed case. Here are written the antipodes and co-units. Now, this is old stuff. Now you add here, using the Heisenberg-Dabu, the cross relations. The cross relations are written here. So you see, comparing with the standard Heisenberg algebra, only in this place you have different from zero element, and also here you have different from zero element. So you have this whole structure on the previous transparency provides you the algebroid framework with 10 plus 10 generators. Now, one can consider different subspaces. So now if in this H1010 you put just the Lorentz parameters equal 1, equal Kronecker delta, you remove spin degrees of freedom from quantum Poincaré group, you get the following algebra. You get the full kappa-deformed Poincaré algebra plus semi-direct product with Minkowski space. It's written here. And this has been called as kappa-deformed DSR algebra, which has been written in different bases in different ways. Here is a covariant way of writing this kappa-deformed DSR algebra. Now, if you remove the Lorentz sector from the algebra H, then you obtain just the deformation of a standard quantum phase space. Now I recall that that these relations cannot be lifted to Hopf, to Hopf algebra, only to Hopf algebroid. Now I'm going to describe you these notions of source and target maps, antipodes, and these coproduct gauges just for this simpler case of standard deformed phase algebra. So now I'm using the property that the target map and source map commute. So now I'm using the canonical choice, such a choice, and solving this equation. I'm getting formulas for target map. One can check that just T is a homomorphic map in Kappa-Minkowski space, and one gets the following explicit form of this left ideal. Now antipodes, also for canonical choice, you get from these formulas, you get formula for the antipodes here. This is the formula for antipodes of x mu. Now, in order to calculate the square of antipode, then you have to use this property here of antipode. And what is interesting that for gamma 0, you don't get square is not equal 1, but is shifted by such a number. So I'm just recalling that generators of base algebra B, I mean the coordinates algebra behaves as unit element in the Hopf algebraic scheme. There is also the consistency relation of the co-unit. And now I'm passing to coproduct gauges. Coproduct gauges, as I said, in Hopf algebroid framework, you can have such a choice of coproduct, but the whole point is that this is not unique choice. Also, you can have a choice where x's are on the left-hand side, but on the right-hand side, you don't have 1. In a canonical Heisenberg algebra, you can have 1. But in non-canonical, you have some non-vanishing f. So you can say that this coproduct shift with added some coproduct gauge gives you this another coproduct. So this is a kind of basic coproduct gauge which changes the axis on the left for axis to the right, or no, in this case, axis to the right to the axis to the left. So you can calculate just from you take this and just from the homomorphism with the algebra, you calculate this basic coproduct gauge. Here are these formulas for this coproduct gauge, and you can check that they satisfy Kappa-Minkowski space relations. And kappa goes to infinity, you obtain a canonical Heisenberg algebra. Now, you can generalize this coproduct gauge. First simple generalization is obtained when you multiply this lambda by alpha. So these are the formulas for the coproducts which you obtain in this case. So this terms proportional to alpha describes you the coproduct gauge. Again, you have a homomorphic map. Now you can introduce the products of these lambdas which you obtained before, just a kind of monomials, and these monomials you can insert into the algebra, and you can show that the homomorphism of coproducts is obtained only modulo the coproduct gauge. It means that if in a given coproduct gauge you calculate the commutator in the algebra, then you get the right-hand side with another element of the coproduct gauge. So we know these things, for example, when we calculate Lorentz invariance of a Coulomb gauge, then you have to change the gauge in order to restore the Lorentz invariance. So up. Okay, so this is the maximal class of coproduct gauges here. Okay, thank you. And here I have written in an explicit way what does it mean that satisfied modulo coproduct gauge. Here you take some two coproduct gauges. The commutator, so it's satisfied here. On the right-hand side, however, is the different gauge. So now the same feature is valid for the coproducts of momenta, which, by the way, this coproduct of momenta are taken from the Hopf algebraic structure of momenta, because if you have x's and p, then B-algebroid structure just leaves the sector of momenta unchanged, but it just modifies the sector of x. Here there's a remark that one can also introduce a left ideal, because I was introducing right ideal, but you have to introduce somewhat different variable y mu. And now we pass to the discussion. So now, what is interesting, is there any physical interpretation of such freedom in coproducts for Hopf algebroids, which is describing the quantum phase spaces? So what is important, that the coproduct gauges are not unphysical as in gauge theories. They just describe model-dependent way of composing two-particle coordinates and momenta. So we have the following conceptual analogy. So in gauge theory, you have a gauge invariant quantities. We have quantum phase space algebra. Here, gauge degrees of freedom are different ways of composing two-particle coordinates and momenta by the homomorphic coproduct formula. And now I will show you how it is realized on the example. So I take the example of free two-particle relativistic phase space. So this is the assignment of the momenta 1 and 2 here in the coproduct. And now, if we consider such a coproduct where alpha describes you this coproduct gauge, then you can relate this coproduct gauge using alpha is equal m1 over m1 plus m2 to the following composition of the positions. So you know that you obtain the composition of a position of two particles in a relativistic system in a way depending on the mass. So this alpha will depend on the mass. So in this way, I'm saying that this is this coproduct just characterize different systems. If you would like to find this composition for relativistic system because of non-polynomial way enters the momenta, so one cannot fit this B-algebroid coproduct unless one introduces some possibility of inverses. Now there is another question still to be considered, because I have chosen the Magid-Rueck basis for this Hopf B-algebroid. So this choice is quite good to derive some covariance properties, and we obtain this standard Quantum-deformed phase space and central extended Lie algebra. So now the B cross product structure is invariant under these transformations. In particular, one can pass to the classical algebra basis of Quantum-deformed Poincare algebra, but in this case you get much more complicated structure of the phase space. It will not have a Lie algebraic structure. So if you want to keep the bicross product property and Lie algebra property, you can only transform linearly the momenta. And here there is a comment that if you introduce dual Hopf algebroids, not every Hopf algebroid is so to say is self-dual. So duality property is valid only for the subclass of so-called Frobenius B-algebroids, and this Frobenius B-algebroids are in that sense important because one can relate them with the property of self-duality, and self-duality which correspond to Born reciprocity in phase space. And this is the end of my talk, and I gave here the references, which are, I'm sorry, I'm just staying in front of you. These are the references. There is a group from Zagreb. They were introducing the B-algebroids, but using only some nonlinear functions of classical Heisenberg algebra. So in this paper, which I present, I use this identification of covariant quantum phase spaces with Heisenberg doubles, and I did show the results were obtained algebraically, so to say. Now I'm giving here some mathematical papers which are important for Hopf algebroids. This is the paper by Takeuchi where the coproduct over non-commutative ring is defined. This is the paper by Lu, and there are some other papers. I think these papers are sufficient to understand well, I would say, the mathematical structure of the algebroids. Thank you very much.
Thank you. Time for questions. Okay, I have one. So
yeah,
in this case, I'm allowed to.
Save the situation. Yeah.
So this Hopf algebroid structure, it's a more general question, I think. It
Yes?
still looks like a groupoid form with the source map and target map.
You mean Hopf algebroid or Hopf algebra?
Hopf algebroid
Yes,
in
yes.
general. So, I mean, with quantum groups and so on, everything gets slightly more general. So is there still some kind of exponential relationship between an algebroid and a corresponding groupoid, or is it?
Yes. You can have. You can introduce groupoids also. Yeah,
Okay.
I mean there is a constructed theory of Hopf groupoids also.
Okay.
Which, by the way, in this paper here, I think, in this paper by Hu or Xu, I think in this paper that there is discussed quantum groupoids. I mean, after discussing quantum algebroids, I'll discuss quantum groupoids.
Okay. And is it known whether the one you constructed, the algebroid, can be exponentiated to a groupoid?
No. The point is that already in Hopf algebra case, when you want to pass from the quantum Lie algebra to quantum group, you cannot exponentiate.
Okay.
You have to do this kind of duality relation. I did show you that you have to take the coproduct from the Lie algebra and dually pass to the structure of the algebraic structure of the quantum group and algebraic sector with the algebraic sector of the. Right. So you repeat this scheme.
Okay.
And of course, because of this source and target map, there are some subtleties in this mapping.
Okay. Any question right now? Any more questions?
I have maybe one comment that there are so-called coalgebra bundles in the I think it was introduced by Majid and Brzezinski. So one can somewhat link this Libya algebroids with these coalgebra bundles.
Okay. Thanks again.